So again, let's have a quick quiz question here about captopril. And we're going to take a look at this thing. It's an ACE inhibitor, which is a type of blood pressure medication. And I'm going to ask you here, after looking at it catalyzing the following reaction, causing angiotensin 1 to become angiotensin 2, that if captopril and angiotensin both contain the amino acid proline, and ACE binds to the proline in each compound, does it make sense to you, would captopril be a competitive or a non-competitive inhibitor of this ACE enzyme that's doing this angiotensin reaction? Take a moment, try and answer that. When you come back, we'll do it on the page. Okay, welcome back. So examining this one here, the real key is what it binds to. So the fact of the matter is ACE binds to a proline that is in each of these things, right? And so that means, at least in theory, unless it's a big coincidence, it sounds an awful lot like if ACE binds captopril the same way it binds angiotensin, well, we know that angiotensin is the substrate, so it's definitely in the active site. If it bonds captopril exactly the same way, sounds to me like captopril goes to the active site. And if that is the case, what we are looking at here is a competitive inhibitor of ACE. And that would be the explanation for the reasoning. Same way of binding, and as a result then same place, in all likelihood, of binding as the substrate itself. One more of these here. We're going to take a look at this propionyl-CoA carboxylase that contains a lysine side chain that gets bonded to a molecule of biotin. And so biotin is shown here below. The big question right off the bat here, the two big questions are, is lysine a cofactor for the enzyme based on what you're reading there? And is it a coenzyme? I didn't get a chance to mention the main difference between cofactor and coenzyme. Let me come back to this one right here. Prosthetic groups in general are cofactors. Coenzymes are the big organic ones. So heme would be a coenzyme under that classification. FAD and NAD plus are both big organic groups. So question now is, then would lysine or biotin fall under either of these classifications? Take a moment, try that out for yourself, and when we come back, I'll have the answers for that as well. Okay, this is number 4 here. I did them slightly out of order because I printed everything off and then decided to shift the order of my slides slightly. But what we can say here is this. A cofactor is any prosthetic group, anything that is not protein but bonds to a protein to help it do its job. So what that means is biotin absolutely is a cofactor. That's the sort of definition. It's covalently bonded to a lysine side chain. It is not protein. It appears to be part of the function. So I would put a check on this. And this is a pretty big organic structure. And so I would be tempted to additionally call that a coenzyme. It's not just simply a metal ion, something a little bigger. Now, as far as lysine is an amino acid. So it's part of the protein itself. What that means is it's not a cofactor, and if it's not a cofactor, it can't be a coenzyme, because this is a subgroup of these, coenzymes being large organic cofactors. Okay? All right, so one last thing before we finish up this video here. Everything we've talked about actually allows you to understand a neat thing that enzymes tend to do, or that enzyme systems tend to do in the human body, which is called feedback control. And the idea of the feedback control is that in many cases, if you have a reaction sequence, you might let one of the early proteins in the sequence be inhibited by the thing that you're trying to make at the very, very end. And so what that might mean is I start with some initial substrate. It gets turned to a first intermediate in a first enzyme. Then that gets turned to a second intermediate, and a third, and a fourth, and finally a product. And if you think this looks like an elaborate way to do something, wait till you see metabolism next week. But what you might do is, if you were kind of trying to design this for yourself and wanted to be able to shut it off when you have enough product, well, you might make E1 something that is inhibited by the product. And so when I build up enough of this, it starts binding to E1, it changes the structure of E1 a little bit, and all of a sudden this first reaction in the sequence doesn't happen anymore. This And then on the other hand, of course, if you need P, if your concentration of P is low, E1 will function well, and the reaction sequence will make what you need, and then you shut it down once you have enough. Pretty neat way, pretty clever way to give yourself something that makes a product when you need it, but doesn't just swamp you with it when you don't. So what we'll be looking at in our next video then is how exactly enzymes can have their activity changed by things other than molecular bonding events. What do external factors like temperature and pH do to enzyme activity? I'll see you when you get to that one.